very good at, RNS and all the different concepts in here. So what we're going to do now is we're going to take a look at these practice problems for chapter 5. And so I'm going to go through them. If you have a question, don't hesitate to stop me at any point, and I'd be happy to answer any question. I'll keep an eye on the chat while I'm going through. But the first two compounds, you can see they're clearly not identical. One's an alcohol and one's an ether, and they both have the same molecular formula. So both are C4H10O, but they have a different connectivity. And so we would say that these compounds are not stereoisomers. They are constitutional isomers, right? They have the same constitution. They're made up of the same atoms, but they have a different connectivity. So there we go. So they are isomers, but there would be constitutional isomers. The next one asks you cis and trans. And remember, with an alkene, you can only use cis and trans when you have two groups on the carbons that are identical. And in this case, we do have two groups that are identical because we have a hydrogen here and a hydrogen down here. And these are on opposite sides of the double bond. And so this would be a trans compound. So we figured that one out. In terms of E and Z, we covered that as well. Now, this question doesn't ask us about E and Z, but if we look at the two carbons, the carbon from the methyl group would take the highest priority on the sp2 hybridized carbon that's on the left. And on the right, it would be the oxygen of the methoxy group. So this compound is a trans compound, but it would also be an E compound, either one. Okay? So if you're wondering, do I have to call the compound cis or trans or E or Z? Well, sometimes we have to call the compound E or Z, but sometimes you can call a compound trans and E. It's totally fine. All right, let's take a look at the next one. It's in the same vein. This is a big molecule, Crestor. It's used to reduce cholesterol, and it's just asking you, based off of this double bond, is it cis, trans, or neither? And hopefully you can see that you have a hydrogen atom coming up here, and you have another one going down here. So those are on opposite sides of the double bond. And so this would be a trans compound. There we go. The next one, remember, when we're looking for chirality centers, so when it says chiral centers, so listen to me very carefully. These all mean the same thing. Chiral center, chirality center, stereo center, asymmetric center, they all mean the exact same thing. And so, we use all of those terms. So chiral center, chirality center, asymmetric center, stereo center, they all mean the exact same thing. So if we go into this compound and try to find the stereo centers in it, remember, we're looking for carbons that are attached to 4 different groups. So you can see that this carbon is attached to 4 different groups, right? You have this carbon here that has 1 methyl. This one has 2 methyls. This one has no methyls on it. And then, of course, there's a hydrogen that's not shown. So that would be a stereo center. If we go to this carbon here, you can see that's a stereo center. It's attached to the carbon in red, which is different than this one, which has some oxygens on it, different than the methyl. And then over here we have a CH2, right? A methylene group. So those are 4 different groups. And then there's one more stereo center in here, and it's this one here, which I think is probably the most abundantly clear one, because you have an aldehyde, an alcohol, then you have an alkene attached to it, and then you have the carbon in blue, which is just an sp3 hybridized carbon. So those are 4 different groups. There are no other chirality centers in the molecule. Just to review, okay, anytime you have a methyl or a methylene, okay, those can never be chiral. Okay, those are never, ever, ever chiral. So you can just put here, not chiral. So that means here we have a CH2, 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 right? CH3, CH3, CH2, those CH3, right? Those are impossible to be, those could never, ever, ever be chiral. And then if you look at the sp2 hybridized carbons, those can't be chiral either because they're not attached to, right? This is sp2, this is sp2. They can't be chiral because they're not attached to 4 different groups, right? They're only attached to 3 things. So there you go. Those are the 3 chiral centers in this molecule. The next one is in the same vein, and this is also another way of representing a carbohydrate. And I'll just go over this one kind of quickly, but if you look at it very carefully, you can see that you've got a chiral center here. We've got a chiral center here. We have a chiral center here. We have another chiral center here. And then we also have a chiral center here. So there are 5 chiral carbons. There's one more carbon, and it's this one here, but that is not chiral because it's a methylene. Any other of them, if you look at them, they're all attached to 4 different groups. Are you talking about this one? Are you talking about this carbon here? 4. The carbon on the left. On the left of the red. So this one here, it's not chiral because it's attached to two groups that are identical. Right? It's got two methyl groups, which are identical. Does that help? Okay. Yeah, so that carbon is not chiral because it's attached to two methyls and they're identical. Yep, so two groups that are identical can't be chiral. Good. All right, let's move on to the next one. It says identify the relationship between these two structures. You got two possibilities. You can either manipulate it in your mind, or you can just designate the stereocenters as R or S. But if you were to take this compound and if you were to rotate it, if you rotate this 180 degrees, what you would get is something that looks like this. So it would look like this, 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 and then you can see that they're identical. Okay, so you can see that these are the same compound. Now, if that doesn't work for you, if you don't like that, so if you don't like that, what you can do is you can designate the chiral centers as R or S. So for the one on the left, the hydroxyl is going to be 1, the ethyl is 2, the methyl is 3. So we go 1, 2, 3 like that. So this is an R compound because the hydrogen is in the back. And for this one, we have 1, 2, 3. So we go like this. So this is also an R compound. So that proves that these two compounds are identical to each other. So, okay. All right. So for the next two, what would be the relation? Can anybody help me out with number 7? What's the relationship between the two compounds in 7? In 7, question 7. Would they be enantiomers, identical? Exactly, they're enantiomers, right? Because you flip the dash to a wedge or the wedge to a dash. Exactly. So these two compounds would be enantiomers. Thanks, Jenny. Perfect. That didn't work, did it? Okay, I'll just circle it like that. The next one says draw the enantiomer of the following compound. All we have to do to draw an enantiomer is flip every wedge to a dash and every dash to a wedge, and we're done. So let's draw the 6-membered ring, which is going to look something like this. Okay, you're going to have to bear with Mr. Dion's work here. But we'll flip this wedge to this dash to a wedge, this wedge to a dash. Oh, jeepers, I'm running out of space already. This wedge to a dash, this dash to a wedge, like that. And the last one is going to be a dash. There you go. Maybe I'll move this a little bit. We'll move it over here. Maybe that doesn't help at all. Anyhow, there you go. So that's the enantiomer. Give me a thumbs up if you're like, I could draw an enantiomer. Flipping wedges and dashes is my game. I can do that. Awesome. I knew it. Okay, next one, just a chirality center. Is it R or S? Kind of a neat compound. It's got 2 hydroxyls in it. We have the hydrogen going in the back. Again, we like that. So this is going to be 4. This will be 1. Now, if we look at the 2 carbons, so I'll put this carbon in blue, this carbon in red. If I look at the carbon in blue, it's attached to oxygen, hydrogen, hydrogen. If I look at the carbon in red, it's attached to oxygen, hydrogen, hydrogen. So we have to keep going. Well, if you look at what's attached to the carbon in red, after the oxygen, or you have the oxygen, which is attached to a hydrogen, but here we have an oxygen attached to a carbon. Well, which one's going to take higher priority? It's going to be the oxygen attached to a carbon because carbon has a higher atomic number than hydrogen. So that means that all of this is going to be group number 2, and this will be group number 3. Now, again, the hydrogen's going in the back, so we go 1, 2, 3. We're going counterclockwise, and so this is going to be an S compound. All right, an S compound for that one. All right, next one is in the same vein. So assign the absolute configuration to this one. So we have the hydrogen coming out in front. So whatever we do, we're going to reverse it. So the hydrogen is here. Sorry about that. The hydrogen is in the back, or sorry, coming out in front. So it's going to be 4. This is 1. This carbon is going to be 2 because it's attached to carbon, carbon, and hydrogen, whereas this one, number 3, is attached to carbon, hydrogen, hydrogen. So here's my tiebreaker. So I'm going to go from 1 to 2 to 3, which is counterclockwise, which would be S, but we flip it because the hydrogen is coming in front. And so this stereocenter would be R. All right, let's keep going. Number 11, Crestor. So it's making its appearance yet again. Okay, it's got 2 chirality centers. Designate them as R or S. So I'll zoom in here so we can see this. The first one, the one I'll use, the first one I'll say is the one on the left. So the hydrogen is coming out in front. The oxygen is going to be 1. The hydrogen is going to be 2. This carbon is going to be, hydrogen is going to be 4. What are you doing? There we go. So this carbon is going to be 2 because it's sp2 hybridized. It's attached to carbon, carbon, hydrogen. Whereas this one is going to be number 3. So we go from 1 to 2 to 3, which is clockwise. We reverse it. And so this stereocenter is going to be S. So I'll pencil this in here. I'll put S. So somebody asked a question. It is, how do you know that the hydrogens are on wedges? Do you mean like this one here? Okay, so if this right, the carbon is sp3 hybridized, right? It's tetrahedral. You already have 2 bonds that are in the plane. You have 1 that's a dash, so that means the last one has to be a wedge. It has to be, right? Because if you have something that's tetrahedral, right, you'd have 2 bonds going like this. If one of them is on a wedge or a dash, then the other one has to be on a wedge. Okay? Yeah, it's tetrahedral. Good. So for the one on the right, just erase this, okay? So for the one on the right, we have the hydroxyl is going to be number 1. The hydrogen is coming out. It's a hydrogen. There we go. So this will be 1. This will be 4. Then we have a carbon here and a carbon here. So the carbon in red is attached to carbon, hydrogen, and hydrogen. The carbon in blue is attached to carbon, hydrogen, and hydrogen. So we have to keep going. This carbon is attached to oxygen, 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 because that's a carboxylic acid. And the one in blue definitely won't be able to beat that. It's attached to, I'll put it up here, it's attached to oxygen, carbon, hydrogen. And so the tiebreaker is right here. So that means that this carbon is going to be 2. This one will be 3. We go from 1 to 2 to 3, which is counterclockwise. We reverse it. And so this would be an R stereocenter. So the stereocenter on the left is S. The one on the right is R. Next one is Plavix, so clopidogrel, which is used to manage blood clots. And so same old thing here. We're determining whether this is R or S. Our proton is coming out. The proton is going to take the lowest priority. Nitrogen takes 1. Then we have this carbon here, which is attached to oxygen, oxygen, oxygen. Then we have this carbon here, the one in blue, which is attached to carbon, carbon, carbon. So this is the tiebreaker. So that means this is going to be group number 2. This will be group number 3. So we go 1, 2, 3. So we're going clockwise. We reverse it. So we reverse R to S. So that means this is an S stereocenter. Next one is, which compound is R2-pentanol? Well, it can't be this one because it's a cyclopentanol. And it can't be this one because this would be 1, 2, 3. This would be 4-methyl-2-pentanol. So we'll scratch that one off. So is it B or is it C? Let's just figure out what B is. So if we put the proton in the back, we would go from 1 to 2 to 3. So we go like this, and that's going counterclockwise. And so this is an S compound. But if we look at the next one, obviously it's the answer. Use the black pen to put the proton coming out like this. So then we have 1, 2, 3, 4. So we go 1, 2, 3, which is counterclockwise, which would be S. But remember, the proton is coming out, so we reverse it. So this is R. And so the answer is C is the correct answer for R2-pentanol. The next one says, give a correct IUPAC name for this compound. So the first thing you have to do is find the longest carbon chain, which has a total of 1, 2, 3, 4, 5, 6 carbons. we have a methyl at carbon 2, an ethyl at carbon 3. So it's 3-ethyl 2-methylhexane. And so we can cross off these two. So now we just have to determine if the chiral center, is it R or S? Okay, so let's zoom in on it. Let's put the proton coming out in front like this. Okay, so the isopropyl is going to be the highest priority because the carbon is attached to 2 carbons. The proton is going to be lowest priority. And then I told you that the longer the chain is, the higher priority. So this will be 2 because it's a propyl, and this will be a 3 because it's ethyl. So we go from 1 to 2 to 3 like this, which is counterclockwise. So that would be S. But again, the proton is coming out in front, so we reverse it. And so this is an R compound. So the answer would be R, 3-ethyl 2-methylhexane for that one. Next one, just what's the correct IUPAC name? Our proton is in the back. The proton is in the back. It's going to be the lowest priority. Remember, the longer the chain, the higher the priority. These are all linear chains. So the butyl group is going to be number 1. The ethyl group will be 2. The methyl will be 3. So we go 1, 2, 3. It's clockwise. The proton is in the back. So that's good. So that means that this is an R compound. So we can cross off these two here. And then the compound, if I number it correctly, it's going to be a 3-methyl 1, 2, 3, 4, 5, 6, 7. So 3-methyl heptane. So R3-methyl heptane for this compound. Number 16, what's the relationship between these two compounds? Well, you can see that they're stereoisomers. They have the same connectivity, but they have a different arrangement of their atoms in space. One of the stereocenters is the same, and one of the stereocenters is different. So what does that mean? Can anybody give me the best answer for this one? They're definitely stereoisomers. Yeah, they're diastereomers, aren't they? Right? Because they're non-superimposable, but they're not mirror images. Therefore, but they have the same connectivity. Therefore, they're diastereomers. Good. Next one is in a similar vein. You see that this chiral center remains unchanged. This chiral center remains unchanged, but then this chiral center is flipped. So what would be the best description of these ones? They're not enantiomers because everything isn't flipped. Only one of them is flipped. So again, thanks, Arubio. It's going to be diastereomers, isn't it? Good. Perfect. The next one just asks you to draw a diastereomer of the compound. There's more than one possible answer. So I'll just draw a couple of them. So we would just flip. Let's make this a wedge, and we'll make this a wedge. Okay, that would be a diastereomer. If I was to, let's see here. If I was to draw a dash and a dash, because it wouldn't be a meso compound because of that carbonyl. There's no plane of symmetry in the compound. So I could put 2 sets of dashes. I could do this and this. Okay, so that would work. There you go. All right. If I was to flip both of them, then that would be an enantiomer. Okay, so these are the 2 diastereomers. So remember, this is not meso, right? So these are different compounds, different compounds, right? It's this carbonyl that throws it off. Okay, so for the next one, it just asks you to draw all the possible stereoisomers. So I'm going to borrow some of my work from before. So I'll just copy these 2 guys. So let's copy this. We'll paste them in here because those would be 2 of the possible stereoisomers. And then if I have a dash and a wedge and a dash. So if I bring this compound, so let me just, what I'll do is I'll paste it a second time. And then what we'll do is we'll take a dash and a wedge. And then we'll do the same thing here. So we'll have our wedge and our dash like that. So those are 4 possibilities, right? You have 2 to the power of 2, which equals 4. And remember, there's no meso compound here, okay? All right, next one, it says, oh boy, which one is the diastereomer of the compound? This one's kind of tough because it's difficult to rotate all of these bonds. I mean, there's some of them you can get rid of right away. So it says if you have this compound, I'll circle it in yellow. So for this one, we said diastereomers. Okay, so I didn't lose that much. Okay, so if I take this compound here, it says which of the following choices is a diastereomer? Well, it can't be this one because it's only got one chlorine in it, okay? So we're looking for something that's a diastereomer of the compound. So instead of rotating all the bonds, I think the easiest thing to do is just to determine whether the stereocenters are R, or S, okay? So if we do the one on the far left, we see that this stereocenter, we go from 1 to 2 to 3 like this. So this is going to be an R stereocenter. So I'll put R for this one. And then this stereocenter here, I go 1, 2, 3. So this one is going to be an S stereocenter like this. The next one, and I'm going to go kind of quickly here, but this one is R, and this one is also R. This one here is S, and this one here is R. So obviously that is, that's not the right answer. S and R. Did I make a mistake on the first one? Did I make a mistake on this? Let me double check this one here. So 1, 2, 3. 1, 2, 3. That's S. 1, 2. I made a mistake on the first one. Nobody stopped me, so this one here. Sorry, I made a mistake on that. That's actually, they're both S stereocenters. Okay, because that makes sense that B is a diastereomer because one of the stereocenters is flipped. And then in D, both of them are S. So this is the same compound as the first one. It's just been rotated is all. So the answer is going to be the first compound and B are going to be diastereomers of one another. Again, it's a little bit of a work to go through all of the R and S, but it's good practice. Okay, very, very good practice to do that. All right, next one. Again, like I said, we're going to skip this one because I would not ask you to do this. I'm just going to write here C, skill builder. It's 5.7. I made a note of this in the textbook. Okay, because in that question, it's one that's in the same vein, but it's something that's reasonable. Okay, this one is not reasonable. There's too many chiral centers in it. So we're going to skip that one. I would not ask something that difficult. Number 22, what's the relationship between these two molecules? I don't know, best friends? No, I'm kidding. Anyhow, so if you look at the stereocenters, you can see that this, if you look at the stereocenters, you can see that this one is flipped. You can see that this one is identical. This one is flipped. And then this one is flipped. Okay, so they have one stereocenter that's the same and all the rest are different. So therefore they're not enantiomers, they're not mirror images. Otherwise everything would be flipped, but they are stereoisomers. And so these two compounds would be diastereomers of one another. It's kind of a rehash of one of the problems that we had before. All right, next one is designate this compound as being R or S. Keep in mind that this is a methyl group down here. So the highest priority is going to be the oxygen. Ethyl will be second, methyl will be third, and the proton will be fourth. So we go from 1 to 2 to 3. So that's going clockwise, which would be R. But remember, the proton is coming out towards you, right? Because it's horizontal. So we reverse it, and this is an S compound. Next one, assign the following stereocenter. So keep in mind that here, there's only one stereocenter, okay? This carbon here is a stereocenter. This one down here, not a stereocenter. How can I tell? Because it's got two hydrogens attached to it. So only the carbon at the top, the red one, is a stereocenter. So this is, hold on. What am I doing here? There's no stereocenter in this comment. I always tell you guys I won't ask any trick questions. Not a stereocenter. It's a crappy question, okay? There's no stereocenter in this molecule, okay? If you didn't pick up on it, it's because this is another ethyl group down here. So there's no stereocenter. Okay, I would not ask you that on a quiz. I would not throw something at you and say, you know, tell me, you know, what's the stereochemical configuration if there's no chiral center. Okay, I'm not going to do that. What kind of person put this question together? Okay, let's try this one here. It says identify the relationship between these. You got two possibilities. You can either draw the Newman projection linear in the plane. So you take it and you put the methyl group. So if I take this compound and I draw it so that the methyl group is in the plane like this, then I would have, come on, Apple Pencil. Then I would have the cyclopropyl over here just like this. Okay, oops, that's not pretty. But then if I rotate it that way, I'd have, yeah, I'd have the chlorine coming out like this, and I would have the hydroxyl going in the back like that. Okay, so you can see that these are diastereomers of one another. They're clearly not enantiomers. But again, you have to go from a Newman projection to, I can fix that up, to a planar projection like this. Okay, so it might take some practice to do that. Another option would be to look down this carbon-carbon bond like this and draw the Newman projection. So you'd say, okay, well, here's my Newman projection. I've got my methyl group, which is at the top, so that's the same. I've got my cyclopropyl down at the bottom, that's the same. On the front, I've got my chlorine on the same side, and I've got my hydrogen on the same side as the one in the red circle. But in the one in the back, I've got my hydroxyl group on the same side of the chlorine. So you can see that these two are not the same, right? They're not there, but only one stereocenter is inverted, and so they'd be diastereomers. Either way works, you know, and I would say there's not one better than the other. I would just go with the one that you're the most comfortable with. Okay, last couple of questions. What is the relationship between the two following compounds? So if I take a look at these two compounds, could anybody tell me the relationship between these? Are they constitutional isomers, stereoisomers, identical, or not isomers? They're not identical in 26, right? They're not constitutional isomers. It's not the best answer. They're stereoisomers, aren't they? Right? These two compounds are diastereomers. Remember, cis and trans compounds. Okay, this one is the trans compound, and this one is the cis compound. Okay, they have the exact same connectivity, so they're stereoisomers. And more correctly, but it's not a choice, but these are actually diastereomers. Diastereomers. Okay, so don't lose sight of that. Cis and trans compounds, if they have the same connectivity, they're stereoisomers. More importantly, they're diastereomers. So for 25, yeah, you can designate this chiral centers as being ROS. That will work too. Okay, but here you can see that this one is identical, and then this stereocenter is inverted. So that way you just know they're diastereomers. You don't even need RNS. All right, for the last one, is the following alkene cis, trans, or neither? Did anybody answer 27? The rule that I went over at the beginning of the chapter. Cis, trans, or neither for 27? It's neither, exactly. It's neither, because when you have two groups on one of the sp2 hybridized carbons that are identical, you can't have cis or trans, right? It's impossible. So there's no cis or trans, right? You could say the methyl group is trans to this fluorine, but it's cis to this fluorine. So which is it? It's neither, okay? It's not cis or trans. The last one just tells you to draw a structure of a compound, R4 ethyl octane. I'll tell you how I do it. What I do is I draw the compound. So 4 ethyl octane. So 1, 2, 3, 4, 5, 6, 7, 8. So on carbon number 4, I'll put an ethyl group. So what I always do is I draw it as a dash, and then I determine whether it's R or S. If it's wrong, I just shade it in. Okay, so that's kind of my way of doing it. So we have the proton, which is in the back, It has the lowest priority. Remember, the longer the chain, the higher the priority. So this is going to be 1, this will be 2, this will be 3. So if I go 1, 2, 3 like that, that's clockwise, which is R. We reverse it to S. So the way I have it drawn is incorrect. So what I'm going to do is I'm going to erase everything that I put in here, and I'm just going to shade that in. So if I shade this in, there you go. There's R4 ethyl octane done. All right. So there we go. So I'm going to post the solutions to these to the chapter 5 module.